So yeah, so today we're going to talk a little bit about okay, so to prove the Dole-Tom-Kahn theorem, all we need to do is verify that there's a long exact sequence of homotopy groups involving free abelian group on a subspace, free abelian group on a bigger space, and then the quotient of the two free abelian groups. And so to prove that, it suffices to show that this quotient map is a fibration, and we'll talk a little bit about that. I wasn't able to prove it, and Math Overflow didn't answer my question. I'm able to prove it in one example. But then so it's like a long story. So then I found a reference proving it's a quasi-fibration, which I'll define today. And quasi-fibration is good enough to get a long exact sequence in homotopy groups. So the plan was for on Thursday to prove it's a quasi-fibration. I found a small mistake in several different references proving that this thing is a quasi-fibration, like dating back to papers in the 70s. But I think I know how to fix it, so I'll read you a false proof. I'll tell you where the mistake is, and then I'll tell you how I think you can fix it. Probably it's slightly too technical to. Well, it depends what people want, but probably I won't fill in all the details fixing it. Yeah, but so, and then we'll begin with like a generalization of the free abelian group on X, where you replace Z with an arbitrary monoid. I think this generalization I think is both interesting and helps us sort of understand the case of the integers better. Yeah. So we want to know. We want to know that the map from Z of X to Z of X mod Z of Y is a fibration when Y is a sub-CW complex of X. That will check that the functor sending a pair of spaces X and Y to the homotopy groups of the quotient satisfies a sort of CW complex version of the Eilenberg-Steenrod axioms, which will imply that that they're isomorphic to homology. Okay, so let's remind ourselves what a fibration is. So a fibration basically is the map of spaces that satisfies the same lifting property that covering spaces satisfy, except the lift doesn't have to be unique. So if we have a CW complex Q, and so you should think of a map from F, a map F from Q cross 0, 1 into B. So you should think of this as a family of paths parameterized by B. So you have a parameterized family of paths in the base space, and then a lift of all the base points to the total space. Then you can lift all the paths. So you have a family of paths in the base and a lift of all of their initial points to the total space. Then you can just lift the path. That's the definition of fibration. And diagrammatically, this is how we write this condition. We have this map F, and we have this map F0 tilde. And the map's a fibration if there exists a lift F tilde. If it's a covering space, this F tilde will be unique, but in general, it doesn't need to be unique. Okay, any questions on fibrations? Okay, and so one nice property of fibrations is if a map's a fibration and you let F denote the so the fiber over a point in the base, you get a long exact sequence of homotopy groups. and we're gonna hope to apply it to the case where E is the free abelian group on X, B is the free abelian group on X, mod the free abelian group on Y. Here Y is a sub-CW complex of a CW complex X, and then the fibers above any point are going to be homeomorphic to Z of Y. So if we can show that this quotient map is a fibration, then we get a long exact sequence of homotopy groups up here, and this exactly just corresponds to the long exact sequence in homology that we're trying to, yeah. Okay, so that's the goal. We won't quite show it's a fibration, but we'll still construct this long exact sequence of homotopy groups, which is all we need. Yeah. Okay. I don't want to have a blank slide. Yeah, so there's a generalization. So let A be an abelian topological monoid. We're going to define a space A of X. So when A is Z, this is be the same thing as the free abelian group on X. So it's defined by the same formula, but you just replace Z with A. So so you can think of it as configurations of points in X with labels in A. The points can move around, and when the points collide, you add their labels using the monoid structure on A. Remember, a monoid is like a group, but you don't have inverses, but you are required to have a strict unit. And we can topologize it. I guess explicit formula is just take the disjoint union of these products and mod out by the relations that order doesn't matter. When 2 points collide, you add their labels, and if something's labeled by 0, the point vanishes. Okay. So so I guess like the point that I'm gonna. Oh yeah, maybe one thing to say is that when A is the natural numbers, this is the free monoid on X. And if you say like I don't know what the free monoid on a set means, well, write down the universal, think like what universal mapping property should free things have. Okay. So the claim is that for general monoids, this this quotient map isn't always a fibration. So to be a fibration, we have this family of paths in the quotient, and we have a lift of one endpoint, and then we need to lift the entire family of paths. Okay, so we're going to take A to just be the natural numbers. We're going to take we're going to take X to be X. Oh yeah, so I'm going to take X to be the interval, Y to be 0. And so we have a map from points in an interval. So this space is the configuration space of points in an interval labeled in natural numbers. This is the space of points in an interval labeled by natural numbers, but the points vanish if they hit if they are located at 0. And then we have a path down here and a lift of one endpoint. And then the claim is that there exists the path here where we can't lift given a choice here. No one said anything in a while, so I'm worried. Maybe I'll move on. Okay, so what path are we going to take? So we're going to have a path. Yeah, so this space is the configuration space of points in an interval, and if the point hits this purple dot, the points vanish. So I'm going to take a path in this space. So just a map from interval. And what I'm going to do is I'm just going to I'm going to send t to a point located at t with label 1. So, what this looks like is just one point moves from left to right. That's the path. And then the lift is just going to be to the empty configuration. So we need a lift at time 0 of this path. That's what f tilde 0 is. So at time 0, this one point is in the purple dot. So there's no points. So the empty configuration is a valid lift. And then I claim, next slide. Oh yeah, I claim that there is no f tilde. Okay, so like I'm sure that I've lost 3 people. One of them should say something to slow me down. Yeah, so I'm claiming that, big picture, I'm claiming that this map is not a fibration by building an explicit path down here and a lift of one endpoint such that we can't build this lift. That's what we're trying to do, and I claim that this is an example of it. Is there anyone who does understand what I'm saying?
Could you elaborate a little more on why the f naught tilde is a valid lift of the endpoint?
Oh yeah. So what I'm saying is, at time, like at time t, the point is located at at time t, we have one point located at t in the interval. So at time 0, we have one point located at 0 in the interval, but we're modding out by the free abelian group on this purple point.
Oh, okay. So it goes away.
So at time 0, this is the same thing as the empty configuration.
Okay, thank you.
You can lift the empty configuration to the empty configuration.
Mm-hmm.
The problem is you can't lift this path because the only at positive time, the only way you can lift, the only lift of this is going to be at positive time, the only way to lift it is you have like a point labeled by 1 here and possibly a point here labeled by question mark. Oops. Why did that delete everything? I don't understand how this works. Yeah, so at positive time, the only way to lift it is to just have one point located at t and possibly something above 0. But upstairs, if you take this path upstairs, like we know what the lift has to be other than like what question mark is for positive time, and then you send like t to 0, and when you send t to 0, you're going to get like question mark plus 1. You're going to get just one point at 0 labeled by question mark plus 1 and no other points. And but our chosen lift f0 is the empty configuration, so we're going to need question mark plus 1 equals 0. And so I claim that like this equation you can't solve in the non-negative integers. You can't solve for question mark. But in the integers, you can solve for question mark.
Okay. Yeah, just because it's just a monoid.
Yeah, it's just a monoid. We don't have inverses. So the point I'm illustrating is like the fact that this map is going to be a fibration uses the fact that the labels are in a group, not a monoid.
Okay,
Um,
thank you.
yeah. Okay, so not communicated a non-zero amount of information to someone, I think. Anyone else want clarification about why, like, when the labels are in a monoid instead of a group, it's not the map's not going to be a fibration, like why this lift doesn't make sense? Yeah, so I mean, if you have any monoid that's not a group, pick some element that doesn't have an inverse, and you're gonna, replace one with that element, you're gonna get this equation, and you won't be able to solve the equation, so the map won't be a fibration.
Jeremy, I have a question.
Oh yeah.
What are you going to show that it's a quasi-fibration? I mean, just for the case of Z?
I'm gonna show. So yeah.
Or more generally,
The general statement is, it's going to be a quasi-fibration. Okay, so I have a reference that's slightly wrong that proves it's a quasi-fibration for any abelian topological monoid with pi0 a group.
Uh-huh.
I think
I believe that's true.
I think you might need some annoying technical condition, like the unit should have a neighborhood that deformation retracts onto the unit.
Okay.
But like no one cares about that condition.
Yeah.
Yeah. So I think, and also, if you have monoids, you can show this map's a quasi-fibration as long as, so like Dold Tom showed they consider the free monoid instead of the free group, but they show that like X mod Z. I can't write. This mapping to N so like let's say that Y contains Z.
Uh-huh.
This is so we have like Z contained in Y contained in X.
Yeah.
They show this map as a quasi-fibration, provided pi0 of Z surjects onto pi0 of X. So you either need your monoid to have inverses up to homotopy, or you need to be working like relative a subspace in both places. So Dold and Tom, they consider.
What does this mean for this example?
Oh, for this example,
you're showing it's not a fibration, but
yeah, it's not a fibration. In this example, it's also not a quasi-fibration.
Right.
Because
But then that needs an argument, I guess. But
yeah, I'm gonna erase what I've written. Yeah, so you're not gonna so in this particular example, this space is contractible, this quotient space.
Mm-hmm.
Because you got a bunch of particles down here, you can just shove them all into the purple dot.
Right.
And then this space, I is contractible, so this is homotopy equivalent to N. So this space is just N, and this space is contractible. And the fiber. Oh wait. Oh yeah. Okay. The fibers N. That looks like this could be a fibration. Let's see. Okay, so the space is N. The total space. Sorry, the space is contractible. Total space is homotopy equivalent to N. Fibers homotopy equivalent to N. Oh wait, so here you do get a long exact sequence of homotopy groups.
But that's not equivalent to being a quasi-fibration,
That's
right?
not equivalent to being quasi-vibration. Yeah, I
Yeah.
thought there was going to be some like group completion thing where
Yeah.
it's a homotopy group to be Z instead of N, and then
Yeah.
I'm going to be able to say like, oh look, it's not a quasi-vibration, but it might actually be in this. I'm slightly confused. I would have guessed that it was not a quasi-vibration,
Me too.
but
Yeah.
it seems like the fibers mapping to the total space is a weak equivalence, which
Mm-hmm.
seems like enough. Yeah. So for people who don't know what a quasi-vibration is, the goal is for me to tell you by the end of today.
But Jeremy, don't you need this criteria around an open set of every point in the base or something like that?
Um,
You know what I'm talking about?
well, there's to prove it's a quasi-vibration, but so I mean the
Oh,
yes. So some people. Okay, so probably at least three of you know what the term homotopy fiber means.
right.
And okay, it's possible those people already know what quasi-vibration is, but so like just to remind Manuel, and quasi-vibration is a map where the inclusion of the fibers into the homotopy fibers or homotopy equivalences.
Right. I see.
The actual
Yeah. And we
fibers, the
have
natural numbers, and I think the
we have these criteria in terms of open sets, open coverings of the base, right?
yeah, there should be a criteria. There should be a criteria that way, but I think the homotopy fiber. The homotopy fiber is going to be the natural numbers, and the actual fibers are all the natural numbers.
I see. Okay.
It'd be a quasi-vibration.
Okay. Okay.
Uh,
Hmm.
but I think that might be an accident here. I'll try to come up with an example where it's definitely not a quasi-vibration.
Okay.
Yeah, but this is definitely not a vibration. And any questions? What?
Hey, Jeremy, can you hear me?
Yeah.
Yeah. So now that I've had a minute to think about it, I have realized that I am confused.
Yeah.
So why is the so the first line that you have, the top one, is saying that since pretty much your purple dot disappears downstairs, then a valid lift is the empty lift. That's what's happening there, right?
Yeah.
Okay. And then where it all goes wrong is that if we want to lift the path, we then would have to go like from the empty path or the empty configuration,
Yep.
and then kind of do a jump and start having things. So
Yeah.
we don't actually get a path.
Yeah.
All right. So that's one argument that I think that it can, it makes sense for me. And then you said something about the monad structure and having inverses. And there you asked me, so how are these two related? Why is this the same argument?
Oh yeah. So well, okay. So what I was saying, one thing I was saying was that this proof doesn't like I'm picking the natural numbers for concreteness, but let's say you have just your favorite monoid. That's not a group. Well, if it's not a group, then you can pick like A in here that doesn't have an inverse.
Mm-hmm. Right.
And then I'm saying you can just do the same thing, label that with A. Same argument will show that it's not a vibration for any monoid that's not a group.
Okay.
So that's one thing I said, and then I'm going to prove basically, in the case, I think the slides have it for Z, but the only thing we're using is that it's a group, that Z is a group, that this map is a vibration.
And what goes wrong if it does have an inverse?
if it does have an inverse, what you can do is you could lift this to A, and then, you know, I guess we're writing additively because they're abelian. So
Yep.
that's what the path is going to lift to.
Oh, okay. Yeah, got it. All right, now it is clear.
Yeah.
Thanks.
So when you have inverses, you know, you can just lift. And yeah, and okay, so I'm gonna go to the next slide and then just say this exact same thing again in the case of Z.
I mean, the path, just to be more precise, the path drags this A.
This A,
Yeah, exactly.
this is the
That's right.
interval. So when time is 0, you have the empty configuration, and for positive time, you have
Right.
A somewhere in the interval, and then a negative A at 0.
Okay, got it. Thanks.
Yeah. Okay. Yeah. So the slide of saying the only way, you know, we could have had an F tilde if we chose F0 to have a 1 there. Great. It's not that relevant. Oh yeah. And so then this is the thing we just talked about, that if we're working with Z instead of the natural numbers, we have we can lift it by, like, for positive time, we just have this point labeled by 1 and a point labeled by -1 over 0. Yeah, so this particular, you know, this, we haven't proven it's a fibration, but we've shown we can lift this one particular path. I'll pause again and see if anyone has questions. And, like, I'm happy to just, you know, someone's like, tell me more concretely what F tilde is. I'm happy to say things like that. Okay, yeah. So in this simple example,
Jeremy, I have a question.
Oh, yeah.
You can ignore it if it's not, if you don't want to spend time on this.
Yeah.
But suppose you have, like, the circle on the base, and suppose you consider, like, the instead of the universal cover of the circle, consider, like, the real numbers, but just starting at 0 and going all the way to infinity.
Oh, okay. So we're not talking about free abelian groups. We're just saying we have.
No, yeah, just like spaces.
Yeah, you're saying, like, we just have, like,
But including 0, maybe.
okay, including 0. So
Yeah. And then you have this projection
yeah.
wrapping up. So is this
Is it
is this still like, is there something that fails here in comparison to the universal cover in terms of, like,
yeah. I mean, well, okay. So
I'm just trying to cook up an example of something that might not be a quasi-fibration, but this might be a quasi-fibration.
well, isn't the homotopy fiber is going to be,
Oh, right.
and the actual fibers are going to be N. You know, and, like, I mean, those spaces are homeomorphic, but the inclusion won't be a homotopy equivalence.
Exactly. So this, yeah. So this is an example of something that's not a quasi-fibration, right?
Yeah.
Yeah. So I mean, this is kind of like the canonical example I have in mind.
Yeah.
And then, I mean, it's kind of related to what you said,
Yeah. Because,
like n versus the integers in some sense.
yeah, I was expecting to get something like this. I was expecting, like,
Yeah, me too. But,
you know, when I'm
yeah.
like, okay, it's not a quasi-fibration, and then I'm like, oh wait, no, I'm proving it is.
Yeah. Anyway, this is a good example for people to have in mind of something that's not a quasi-fibration. But if you consider minus infinity, then you get a quasi-fibration, right? So
Yeah. I'll try to like embed this example into configuration spaces for some future.
Okay. Yeah.
Or whatever these generalized configuration spaces. And also like once we talk, once I define quasi-fibration later today, people can feel free to like ask like if they care, like what were we talking about right now? Okay. Yeah. So I think this.
I guess we haven't defined quasi-fibrations.
Yeah, like it is.
Oh yeah.
People can also look at later slides on the website, or just wait until till later slides. Okay. Yeah. So typo. Want this to be a Q, and I forgot like a cross Q. Okay. Yeah. So I'm proving that this is a fibration. So basically, we're just gonna do what we did before. I mean, the idea is, we use the same ideas we had before. Basically, we have stuff that appears out of zero, and what you want to do is, if stuff appears out of zero, you add the inverse of that stuff sitting at zero upstairs. Okay, so let's see what I wrote. So, we have this family of paths parameterized by Q in the base, and then in the total space, we have a lift of their endpoints. And so I'm going to have two functions. So G is going to measure the sum of all the labels in Z of I, and H is going to measure the sum of all the labels, G is going to measure the sum of all the labels of points in I, and then H will measure the sum of all the labels of points in the half open interval 0, 1. And so, G is a continuous function, whereas H is not a continuous function. Yeah, so go to the next slide. Yeah, so H of this configuration, assuming I added these numbers correctly, is 7 plus 1 plus negative 13, which negative 5. So H is not a continuous function because this point labeled by 7 could enter the purple dot and vanish. And then this F tilde Q, this map here, except I forgot to write Q's here, is going to be so what we're going to do, we have this map F here. Off of 0, we're sort of forced to have F tilde be the configuration that agrees with F. So that's what we're going to do. And then the question is, what are we going to label 0 with? And we're going to label 0 with F of Q minus H of too many typos. Label this with G minus. Okay, that's impossible to read. So, okay, what is this illegible thing? We'll write it. G. Oh, is there a text I type? Yes, this that's better. Okay, this is G of F of Q minus H of F of tilde F0 QT. So the formula for the lift is, we have some configuration space downstairs, we want to lift it upstairs. And so, you know, we have a bunch of points. They're doing whatever up here. So we lift whatever is happening down here, up here. And then the only question is, what are we going to label this point with? And we label it with this number. And that just, if I did this correctly, this should measure like this number here should, in the in this example, give you -1 for positive t. So, you know, like in this example, what are we gonna? How do we lift? Well, we lift with you know, we're forced on the half open interval to just lift whatever we have downstairs, upstairs. And then the question is, what do we label 0 with? And what we're going to do is we're going to label it with basically this -1 is the difference between like how many points are in the half open interval at time t, and how many points we're lifting, and like how many points we lift you know, or I guess, and the sum of all the labels of f tilde. Any questions? Sorry for the, it's hard to jump slides with all the typos. We're just trying to come up with a formula, like, what is this -1? I'm claiming that this -1, you know, -1 is 0 minus 1, which is a great formula. But what am I saying? I'm saying 0 corresponds to the fact that f tilde, in this example, is the empty configuration. And -1 corresponds to the fact that f at this particular time has 1 point in the half open interval. I'm not sure that I like super care if people actually followed this formula, but I mean, you know, the idea is this picture. But I'm happy also if someone like actually wants to understand the formula that I wrote down to try to explain it. Yeah, so I mean, just the only mystery to constructing the lift is what do you label this point with? And I just, you know, you can just write down a formula in this case. Okay, so I believe in general that this map is going to be a fibration, but there aren't any references, and it seems hard to just write down an explicit formula. Like anything you can think of seems to lift, but yeah. So if anyone sees how to by hand prove this map's a fibration, like we should write it up and send this to some like quasi-expository journal. Okay. So I don't see how to prove that this is a fibration. So we're going to try to prove it's a slightly weaker thing called a quasi-fibration. It's probably a fibration, but okay. And you know, I guess unfortunately my reference proving it's a quasi-fibration has a mistake, but I think it's still fine. Okay, so you know, what's the idea of a quasi-fibration? The idea of a quasi-fibration is you ask yourself, like, what should the fibers be if the map were a fibration? And then you say that the fibers need to be homotopy equivalent to what the fibers should be. That's the definition of a quasi-fibration. Okay, to make it rigorous, I'm going to tell you how to replace a map with a map that's a fibration, where so we have a map from A to B. We want, that's probably not a fibration. We want to replace A with a space that's homotopy equivalent, such that the map is still or making the map a fibration. So this will not change B. It'll change A, but only up to homotopy. But it will definitely change. It will likely change the fibers, and it'll potentially change the fibers up to homotopy. So it won't change B at all. It'll change A up to, but only up to homotopy. But it might change the fibers. So we're going to build this space EF. So it's the points in EF are going to be elements of A and paths in B. So it's a point upstairs and a path downstairs, such that the path, one endpoint of the path, is f of A. And then we have this has a map to B, which is just evaluate the path at 1. And so then the claim is that there's an obvious projection from EF to A that maps a homotopy equivalence, and this new map P is a fibration. And I guess like diagrams commute, so this map P is in some sense equivalent to the map F. Yeah, any questions, like either philosophically what we're doing here, or like concretely what these definitions are? Yeah, so we're just trying to replace an arbitrary function with a fibration. Okay, so let's prove that EF to A is a homotopy equivalence. And yeah, there's a good chance at some point I will confuse 0 and 1 somewhere. Okay, so what is EF again? So it's the set of points in A and paths in B, such that the one endpoint to the path agrees with f of A. I have a picture. Maybe I should have drawn a picture. Yeah, so I mean, you're just sort of thinking, you have B down here, you have A up here. And so, if you have this point A here, what you're thinking of so an element of EF is a point in A and a path in B, such that this point maps to that point. Okay, so there's a map from EF to A where you just forget the path, and then there's a map from A to EF where you send it to the constant map at constant path. This should be f of A. Typo. Yeah, so if you have a point at A, you can assign it to an element of EF where you just take that point in A and then the constant path at the image. Okay, so one of the, the inclusion of A into EF followed by the projection is the identity. And so now we're trying to show that the other composition is homotopic to the identity. And So the other composition takes your element of EF, forgets the path, and then replaces it with the constant path of the image. So yeah, so what do we want to do? We want to we want a homotopy of EF that on this element sends, or we want a homotopy between the identity and replacing all paths with constant paths. Well, how do you do that? If you have a path, you can just, shrink the path down to a point. So here's a formula. So the homotopy just, the homotopy takes this path and shrinks it down to a point. And that's the homotopy. Yeah, so any questions why EF is homotopy equivalent to A? So this is sort of a parameterized proof that like the path space is contractible. Okay. And then the next claim is that this map P from EF to B is a fibration. So EF, and this map P sends a point in A and a loop to gamma of 1. And I wrote down some formula that's probably wrong for so we want to prove this is a fibration. So I don't know why I switched it to G. Okay, we have because the map is called F. That's why I switched it to G. Okay, so we have a family of paths in the base and a lift to the fiber, and we want to lift that that to a path. And sort of the idea is like everything is paths, so we can find paths. Okay, so I at least would never be able to understand this formula in real time, so let's look at a picture, and then if someone wants to go back to this formula, we can. Okay, so for pictures, we'll just take Q to be a point, so I'll tell you how to lift one path. So what is this picture? We have, so what is, maybe I should have written a 0 here, so we have G tilde 0 point. It's just going to be some point in EF. So what is that? It's an element A and a path gamma. And then what is G? So G is a path in B, right? And a lift at time 0 is a point A and a path in B. So the black and the red are the lift, and the blue is the path. It's a little bit confusing because everything is a path. So we want to so we have a path downstairs. So we have this path G downstairs, and we want to lift it to a path upstairs. And what do? Well, so at time 0, we just have this red path. And at time, for positive time, what we want is we want a path that sort of goes along the red and then goes along the green for part of the green. So we want to sort of go along the red and then the blue, and you have to reparameterize things. Okay, I'm not saying this well, so someone should attempt to ask a question to help me out. Because I should say this again. Yeah, so maybe let's even remake the diagram. So we have, we have EF, and we have B, and we have G from the interval into B. Oops. G, the interval 0, 1, B. Is not using. Yeah, so what and then we want to build this diagonal left. And remember, this space is the space of points in B, or sorry, points in A and paths in B. So we have a path in B, and then this is another path in B. And we want to lift making the diagram commute. So that, like at time t, we want a path downstairs that when you evaluate it at 1, gives you g of t. So that's why we sort of take this family of paths that starts out in the red and ends up in the blue, ends up in the red concatenated with the blue, or g tilde. Any questions or requests for clarification?
Yeah, so in this picture, what is given and what is a construction?
Oh yeah, so what's given, I'll just erase everything. What's given is g tilde and g. So g is a path in B, so g is the blue line.
Yeah.
G tilde is a point in EF. A point in EF is this point A, and a path in B. So
And why do we know that that path that we get meets G like that?
Yeah. So so we're given. Yeah. So we're given all of this, and then we need to find this g tilde making the diagram commute, and what that amounts to is a family of paths interpolating from the red to the red concatenated with the blue.
Okay, yeah, but my question is, how do we know that the red path and the blue path meet at a point like that?
Yeah, so that's what like g tilde is a lift. G tilde 0 is a lift of g evaluated at 0. And if you say what that means, so
Yeah, okay, so if you map it through F, I guess, then then you get
yeah, so this is the so the fact that they meet at this point is that this diagram commutes. This diagram commuting, I guess here Q is a point. This diagram commuting is the statement that so it's funny, sort of we're interpreting a point up, a point up here has a path, and a path here is a path.
Yeah.
And the fact that the diagram commutes means these paths, that means that gamma of 1 is g of point comma 0. drawing the picture in the case Q is just. And then this
Okay.
this lift is just an interpolation between the red and then the red concatenated with the blue plus the point A.
Okay.
So you just
I think I got it. Yeah. So that last equation, gamma of 1 equals g of point at 0, that is basically saying the endpoint of gamma is the starting point of g.
yeah.
G, I mean the path, not the, yeah, the path.
Yeah.
Yeah.
Yeah. And
Okay.
like that involves the function p going from EF to B. So just unwinding what that means.
Mm-hmm.
So yeah, so what we've sort of done is we've replaced A with a space that has all this contractible path data. But this contractible path data means we can lift anything, basically. Like how do you lift a path? Well, we've sort of just thrown in paths into A. So you can, EF is a replacement for A. So in EF, we just have all this extra path data. So then we can lift things for free. But we haven't changed the homotopy type. Yeah. Any other questions before I move on? Yeah, so the definition of the homotopy fiber is, we have this map F from A to B. The homotopy fiber over B is just the actual fiber of this of the map P. So what you do, the homotopy fiber is, the way you can construct the homotopy fiber is you replace F with this map that is a fibration, and then you look at the fibers of that map. And inclusion of A into EF via constant maps induces a map from the actual fibers of F to the homotopy fibers. And then we say that a map is a quasi-fibration if the map from the actual fibers to this homotopically correct fiber induces an isomorphism on homotopy groups. So if everything's a CW complex, we're saying that the fibers and the homotopically correct version of the fibers are equivalent. And anything I should repeat? Yeah, and so one thing to say is if the map's actually a fibration, you can show that if the map's if the map's a fibration, you can show that the fibers are equivalent to the homotopy fiber. Okay, so then the proposition is that if the map's a quasi-fibration, then you get a long exact sequence of homotopy groups. So it doesn't need to be a fibration. You get a long exact sequence of homotopy groups. It could just be a quasi-fibration. And the proof is just, well, replace your map with a fibration. That's a fibration, so you get a long exact sequence of homotopy groups. But now you just observe that like pi I of EF is just pi I of A. And because it's a quasi-fibration, pi I of the homotopy fiber is pi I of the actual fiber. So the long exact sequence in homotopy groups for EF to B, that just agrees with the long exact sequence we're trying to construct. Yeah, so you should sort of think of quasi-fibrations as being something close to the minimal condition needed to, or basically it's the minimal condition needed to get a long exact sequence of homotopy groups.
Jeremy, can I say a comment?
Oh, sure.
That in the definition of quasi-fibration is not enough to ask that these two things have the same homotopy type, right? You want the inclusion map to be a weak homotopy equivalence.
Yeah, you want this map.
A counterexample, yeah, exactly. A counterexample is that thing I said earlier, right?
Oh yeah. So in Manuel's example of, like look at the universal cover of R mapping to, or universal cover of S1, so R mapping to S1, but you replace R with some subset like the non-negative real numbers. There, the fibers will be in countable discrete sets, and the homotopy fibers are Z, which are countable discrete sets. So the fibers and the homotopy fibers are homotopy equivalent, but the natural map is the inclusion of the natural numbers into Z, which is not a homotopy equivalence because it's not surjective on pi 0. Yeah, so in particular, I guess I didn't write IA star, but I mean, like, if this map's an ISO, not just there is an ISO. Okay. And then, the theorem we're going to prove, modulo some issues I found in my reference, in the reference I was using, is going to be that if A is a topological abelian monoid and Y is a sub-CW complex of a CW complex X, then, and pi 0 of A is a group. So in the case that A is discrete, I'm just saying A is a abelian group. Then the map from A of X to A of X mod A of Y is a quasi-fibration, which will give us a long exact sequence of homotopy groups. Yeah, I think that's all I had. And then, so on all these slides, I put homework. I'm happy to talk about homework or read homework if you do it, but I'm not enforcing grades. Okay, yeah. So I think that's all I prepared for today. Maybe I'll stop the recording.